Undergraduate Academic Symposium. My name is Stan Zygmunt, and I'm the Assistant Director of Student Research here at Valpo. This week we finished a challenging and difficult semester in which the unexpected transition to remote learning tested us all, students and faculty alike. The separation from campus was felt even more keenly by students who were in the middle of research projects. Today we meet to celebrate the completion of these projects by very talented and dedicated students who I'm proud to be associated with. Today's events include an opening address, 3 sessions of student presentations, and closing remarks. I encourage you to attend as many of these as you can. And I also ask that at the end of the day, you fill out an evaluation form that can be found at the bottom of the conference schedule webpage. We don't know if we'll be doing this again online, but we value your feedback on this conference. Right now, I'd like to turn it over to Brett Vester, who's our meeting host, for some housekeeping.
Just a couple items of note. I will be muting everyone except for Laura for her presentation. And then at the end, if everyone could use the raise hand function, which you can find in the participants pane to the right. If you don't have it enabled, it's the 4th icon kind of in that floating menu that sits on the bottom of your window. If you click that, then you'll be able to see you. And then to the right of your name, you'll be able to see that raise hand function. So if everyone can use that, then I'll go in and unmute those people, have them ask their questions. That way we don't have a bunch of people unmuting and causing an echo cyclone. So other than that, we are recording this session just to let everybody know. So just make sure you're comfortable with that. Other than that.
Thanks, Brett. Today's events, our opening speaker today is Professor Laura Pudwell of the Valpo Department of Mathematics and Statistics. Professor Pudwell is a 2003 Valpo graduate who continued her studies at Rutgers University, where she received the PhD in mathematics in 2008. She returned to Valpo as an assistant professor in the fall of 2008 and is currently associate professor of mathematics. In 2013, Professor Pudwell received a Math Faculty Mentor Award from the Council on Undergraduate Research. She also received the Henry L. Alder Award for distinguished teaching by a beginning mathematics faculty member from the Mathematical Association of America in 2014. In the last 12 years, Professor Pudwell has directed 14 undergraduate research projects involving 41 students. All of these projects resulted in oral or poster presentations at professional conferences. Of her 35 professional publications, she's published 10 refereed journal articles with undergraduate students as co-authors. This is a remarkable record for a faculty member at a primarily undergraduate institution like Valpo. Professor Pudwell is co-author of the book, A Mathematician's Practical Guide to Mentoring Undergraduate Research, published in 2019. I cannot think of a better person to speak this morning on the topic Discovery, Inside and Out. Join me in welcoming Professor Laura Pudwell.
Thank you, Stan, for that kind introduction. In just a moment, you should see my slides too. All right, and thank you to all of you for signing in. I know it's been, like Stan said, an unprecedented and kind of exhausting semester, and yet you are a couple days after finals are done, signing in for another day of academic activities. And I think that speaks a lot to A, your commitment as students and faculty to celebrating student work, and just B, commitment to a community that really likes interacting together and celebrating good work. And so today I'm going to talk about discovery on a few levels that I think happens through research, but I feel like I can't get started with this talk without acknowledging this, which, even though you can't see it with the naked eye, has kind of turned our last few months upside down. Whether it's your daily schedule getting changed, or what your classes look like getting changed, or as I've browsed through some of the projects on the SOURCE website, I've noticed some of you have had to adapt parameters of your project because of changing access to resources you were expecting to use. And it's definitely changed our format today. And I think one frame I've heard a lot of people use in the last couple months is to list off all the things that they're frustrated or disappointed have changed. But I think there's a different frame worth discussing today, even about the time of living with the coronavirus in our communities. And that's when you're thrown into a new situation, it's an opportunity for a lot of discoveries on a lot of levels. And so first, let's unpack this in the Corona times era, and then we'll focus on undergraduate research after that. I think it's easier than ever to find the word discovery in news headlines right now. Maybe the first ones that come to mind have to do with the medical field. You have people doing all kinds of studies and collecting data to better understand this coronavirus and what might be effective ways to treat it. And research doesn't happen like, here's a flash and here's the final answer. It kind of happens in fits and starts and kind of converges on a solution to a problem. And so we see a lot of exciting things going on in the natural sciences and in the medical field right now. But you don't have to be in a hospital or clinic or lab to be thinking about discoveries with COVID-19. One of my favorite headlines from March was actually this. I have friends at Oak Ridge National Lab in Tennessee, and Oak Ridge National Lab put one of their biggest, fastest supercomputers to work fighting coronavirus. You might wonder how that works when it's not directly interacting with patients, but basically it knew the chemical structure for thousands of chemicals, and it analyzed which 70 or so might be most promising for lab tests. So it acts kind of as a sieve to help people in lab settings that are working actually with chemicals to better narrow their focus more quickly. And maybe you're not interested as much in the natural sciences. I think there's still a lot of discovery to happen in other contexts. I love this quote here from a professor at Carnegie Mellon University from within the last week or so. Humans are so fascinating, and that's why I study them. If you'd rather study institutions and human interactions, you've got vast new data sets to work with now with all the things that have changed in our daily lives in the last couple months. And there's models for that too. Even if you don't want to think about it qualitatively, quantitatively, people have been making models to see the effects of how our behaviors work together with disease spread. And I'm trying to hit on all kinds of disciplines here. So far we've talked a little bit about discovery in natural sciences and in social sciences. I found it exciting that this digital humanities review I found online had to add a whole new section just because of the research that's coming up in the COVID-19 era. And even in the visual and performing arts, you see people who are used to performing together finding new ways to use technology to safely perform, but from their own homes, including our own chorale and cannerai. And maybe you wouldn't call the work you're doing research, maybe you'd call it more creative work, and then maybe the virus could be a source of inspiration. What I think is kind of poetic about this is the chocolatier that's designing Corona-themed Easter eggs is actually the Louis Pasteur chocolatier in France. And if you're familiar with Pasteur's work, he was one of the people who first showed how germs help with disease spread. And so the fact that Pasteur Chocolate Shop is now making the disease-themed chocolate, I think is just kind of humorous. But of course, discovery that's not related to coronavirus hasn't stopped. An exciting headline, if you care about astronomy, from the last couple weeks is we found the closest black hole to Earth that we've found yet. And so there's all kinds of discovery in the headlines. I think there always is, but to me at least, right now in a season of change, it's even easier to spot the discovery in the headlines than it was before. And I think headline level discovery is not the only kind of discovery going on right now. I took an informal survey of some of my friends and asked them, what have you discovered in the last couple months of changing your schedule and having to work from home? I know there's a lot of stressors, but what are some positive discoveries? And this is a word cloud of their responses. I won't read all of them, but what strikes me the most is the word that shows up biggest and in the center here in dark is learning. People are learning all kinds of things based on having to change up their schedules. And I'll share a few highlights that I think set a good stage for the kind of thinking I want to do later in this talk. A friend who lives in Chicago says, I've discovered how much nature there is to explore and appreciate, even though I'm in the middle of a giant city. And that's something that without changing the context and the setting of her work a little bit, she might not have realized. A Valpo alum said, I'm better at baking than I thought, and I'm only getting better while this goes on. So new context gives you time to work on new skills. The next two are a little bit more academic focused. Although you might be thinking, yeah, I've been spending a lot of times on screen lately and I could use a little bit less. I have a friend who noticed a benefit in this, who says, I'm excited, I'm going to be able to attend more conferences than I ever would have thought before, because now they're virtual and you don't have to be making decisions based on time and travel money. You can go, I can turn on my computer and connect and learn new things. Maybe you're discovering things you appreciate by their absence. As one faculty member pointed out, not being there makes me realize just how much I really do appreciate my office, my campus, and my face-to-face colleagues and students. I've got one more round of quotes to share that I think also fit nicely with today. A couple people who are home with their kids are getting a whole new appreciation for learning that they weren't seeing coming. One says, I got to teach my 4-year-old to read, and watching someone learn to read is awesome. And another person listed all the crazy questions their small children are asking, but then says, I've realized anew just how beautiful the inquiring mind is. And so I think while we're living in a very stressful semester right now, there is a lens that it's also a great time for discovery, both on kind of the news headline level and on the personal reflection level. So when you're thrown into a new situation, it's a great way to discover things on a whole lot of levels. Well, today is really a day to celebrate discovery. And I know we were expecting it to look a bit more like this in the Union. It's actually really exciting if you haven't experienced the in-person version of SOURCE before, to walk in and see the ballrooms packed wall to wall with presentations that represent all of campus. And the room is literally buzzing with all the conversations. But I think as the university was looking at what did we need to cancel and what did we need to adapt, SOURCE was never on the cancel list. It's had a variety of names over time, but it's been a very valuable part of end of year routine for a long time. In fact, here's student me getting all excited to present a math poster before we had kind of the nice printers we have now. This has been going on for a long time, and for a lot of reasons, the university values the student work that we feature today. We'll get into more of the reasons the university so cares about undergraduate research a little later in the talk. But on a personal note, I can say working on projects like this throughout my time at Valpo has been absolutely one of the highlights of my job here. You get to know the other people working in a project more closely than you would in a classroom setting. And you get to work on fascinating things that you wouldn't otherwise see in a classroom. And so these are all my research teams from the past 12 years from before this year. And one thing you should notice in every single picture here is a research poster. I think this day is also an important step in your undergraduate research project experience. When you're going through it week by week, it's really easy to be focused on specific details and just kind of narrowly focused, even if you know you're doing a bigger project. But there's something about having to summarize it and lay the whole story out for someone else to understand that I think gives you a better appreciation for the range and the scope of what you've actually accomplished this year. And so what I'm going to do with the next part of this talk is feature one of these groups, this one that just lit up in green. I'll tell you how I picked them on the next slide. But there's a couple things you could be doing as I'm about to tell you a math research story. I think it's a great math research story, and I've been careful to try to keep it visual instead of lots of technical notation. And so you could actually be following the plot line of the math story. But at the same time, I think a research situation is one of these times where you're thrown into a new context, and it's an opportunity for discovery on a lot of different levels. And so no matter how closely you're following the math story, the other thing I'd encourage you to think about is what are the other levels of discovery that are maybe going on in this story that you wouldn't see on the poster. So let's get started with our story. I'm going to tell you about this team. This is a poster that was presented at SOURCE in 2018. It actually has my favorite title I've seen students put on a poster. You can't read it, but it says Fantastic Patterns and Where Not to Find Them. And I picked this team for a couple reasons. One of them is it's a great math story, but another is, other than Ryan over here in red who graduated last year, this features 4 current 2020 Valpo seniors, and it seems appropriate as we wrap up this academic year to acknowledge the work of some of our amazing seniors. Another thing that's interesting about this team is, although they're all math majors and all love mathematics, I think they love it for different reasons. And so they brought a lot of different perspectives. And you even see that as you look at what they're doing after graduation. Two of them are going into secondary education. One's been applying for graduate programs, and two are going straight from graduation to work for companies where they'll develop software. And so that's some context of this team, but now let me tell you about their mathematics. This group thought about permutations. And if you take a math class that talks about permutation, this is probably not the picture you see. A permutation is usually defined as a list where the order matters. But I'm trying to keep this visual, so this is what I picture in my head when I think about a permutation. This is a grid where there's a bunch of dots, but notice the important thing is each row has exactly one dot in it as you read across the rows, and each column has exactly one dot as you read across the columns. So this is kind of a visual way of representing the definition of permutation I gave a moment ago. And when you have a big permutation, and you think about it in terms of these dots, there's actually a lot of little permutations inside of it. So for example, 3 of those dots just turned orange. And if I focus on just the 3 columns and 3 rows that have orange dots, I really get this smaller permutation inside of it. Notice that of the orange dots, the lowest down one comes first, the highest up one comes second, and the medium size one comes last. Small, large, medium. This orange permutation is inside the big permutation using those 3 dots. So if you've got that definition, you have enough to know what to look for on the next slide, where there's about to be a lot of permutations. Here are all the permutations you can make with 4 dots. There are 24 of them. If you want to think for a moment about why, remember there's 1 dot in each row, 1 dot in each column. And so if I'm drawing my permutation 1 column at a time, I have 4 choices for where that first dot could go. It could go lowest, second, third, or fourth row from the bottom. But once I've put 1 dot in the first column, I only have 3 choices for where to put a dot in the next column. And once I have the first 2, I only have 2 choices for the third column. And then the last one's decided. 4 times 3 times 2 times 1, 24 permutations of size 4. But now let's tie in this definition from the previous slide. So what if, for some reason, I only cared about permutations that don't have this red shape inside them and don't have this orange shape? And we'll get to why in a minute, but first let's practice with our definition. I'm going to throw out every permutation where I can find 3 dots that appear in increasing order. Well, that throws out these 10. There might be more than one way this red permutation is inside of them, but inside of each of these 10 red permutations, you see a small, medium, large kind of permutation inside. I'm also going to throw out ones that have this orange permutation inside, and that throws out 6 more. These are ones that have a small, large, medium thing going on. So if for some reason I only care about permutations that don't have this red shape or this orange shape inside, I've narrowed down my work to focusing on just these 8. And so let's focus on those. You might be wondering, why in the world would you do this? What's your application? And I'll point out I'm a pure mathematician, and so the question I have an easier time answering is, what's my motivation? The motivation for this project is I just told you the definitions you need to know to understand this theorem by 2 mathematicians from 1985. And I realize if you're a student, that's older than you, but in the scheme of mathematics, that's actually pretty recent. And this theorem says, if you care about permutations with n dots that don't have this red shape or this orange shape inside, you're going to get exactly this many permutations. So these were permutations of size 4. Notice we have 2 cubed or 8 permutations that follow the rules. You might still say, great, that sounds mathy. Why did they care? Well, they cared because there are a bunch of results in theoretical computer science about sorting algorithms in the 60s and 70s. And they had read those results where permutations inside of permutations mattered and said, hey, we can answer some counting problems. So then continuing the story from sorting algorithms to some mathematicians answering counting problems, we said, cool, we know how many permutations don't have this red shape or this orange shape inside, but maybe we can describe those 8 permutations a little bit better. And so you could play connect the dots here and kind of from left to right, connect the dot in the first column to the second to the third and so on. And notice sometimes these lines go downhill and sometimes they go uphill. So you might ask questions like, how much of the time do you expect to have ascents or uphill going lines versus descents, which are downhill going lines? Or you might ask, how many peaks do you expect to see in these permutations? A peak being a dot like this that's bigger than both of its immediate neighbors. And while the students could collect all kinds of data, I could write these 8 permutations and list how many ascents, descents, peaks, and valleys are in each one. If you want to understand what's going on as the permutations scale up, it helps to change your perspective. And so I'll show you a clever way the students change their perspective to answer these kinds of questions. I'll show you a little bit what the results look like, but again, keeping it pretty visual. How do you change your perspective when you can see the peak right here? Well, it turns out that's actually not the best way to write these permutations if you want to answer a how many question. It turns out it's better to take your permutation and actually write a list of letters that kind of encodes it. So here's one of these permutations that doesn't have the red small, medium, large shape inside of it, and it doesn't have the orange small, large, medium shape inside of it. And over here on the right, I'm going to draw the exact same permutation one row at a time, starting from the top and going on down. And so far I have my dot that goes in the top row. Notice that the one that's in the second from the top row was to the left of that blue dot. And so are the next two. So I'm writing L for left, for this was to the left, this was to the left, this was to the left of our original dot. The next dot was to the right of our original dot. And now I'm going to highlight it in blue because it's the new rightmost dot in our graph. And so the next dot was to the right. It's our new rightmost dot. Then we went to the left, to the right. That's our new rightmost dot, and to the left. You've seen that once now, but that's a little bit weird the first time. So I'm going to go run through it one more time. Notice that I'm taking this permutation, I'm doing it from the top on down, and I'm paying attention to whether each new dot is to the left or to the right of the last dot we've seen so far. So here it is just one more time. That was the dot in the first row. The first 3 dots go to the left of it. The next one goes to the right, and that's our new rightmost dot. The next one goes to the right, that's our new rightmost dot, to the left, to the right, and to the left. And you can store those details if you want to ask specific math questions at the end, but you're really fine if you just say, okay, there was a way they took these pictures and made them match up with lists of L's and R's. And so on the next slide, what the students actually did to answer our more nuanced questions about these permutations was they took each of these permutations where you can actually visually see going uphill or having a peak, and they wrote down the corresponding list of letters, the L's and R's. In fact, I saw a number of people from Math 266 already on the participant list. What they found here was a bijection between the permutations here and these lists of L's and R's. And then anything we wanted to ask about these permutations is also a question we could ask about these lists. And so looking for the number of ascents or uphill lines in these pictures actually matches up with the number of times you see an R immediately followed by an L, plus one more if you start with an L. So for example, these 3 down here each have an RL, they each have 1 ascent. These 3, the 4th, 2nd, and 1st one in this row, each start with an L. They have 1 ascent. This 3rd one in the top row actually has both things going on. It starts with an L and it has an RL, so it has 2 ascents. So realizing that way to look from a new angle actually allowed us to answer a counting problem. Similarly, the number of peaks, which you see highlighted in green now, those matched up with the number of LRs we saw in these lists. And so the only technical slide you're going to see that actually has intense math notation is the next one coming up. By looking at these permutations from multiple different angles, the students were able to answer all kinds of questions. This is just a subset of the results that were on their SOURCE 2018 poster, but you were focusing on things that have neither of a small, medium, large, or a small, large, medium kind of shape inside of them. And the students were able to count the number of permutations of size n with exactly k peaks, or exactly k ascents, or all these other features. And they were able to do it no matter which 2 patterns or permutations of size 3 you didn't want inside of your picture. That's a lot of work. So then what happens next? Of course, they presented at SOURCE. You saw the picture of them with their poster for that. And when you present at SOURCE, you've actually made your work publicly available for other people to look at, because now you have your abstract and your poster and the share your audio file all on a website, on a university website, outward facing to the world. That's pretty exciting. But this team kept going, actually. 3 of the 5 kept working over the summer, figuring out more and more results, and they presented a few more times, both on campus and at other conferences. And eventually we had enough work that we published a research paper together, which appeared in the Journal of Integer Sequences last year. And so having a publication is another way that your work goes from campus and out into the world. And it gets even better than that, because just as we based our work on the work of previous mathematicians, we've already started to see some other mathematicians citing our work. The first paper that cited ours, I wasn't surprised about. It came out about the same time. It's by a mathematician in California and 2 of his graduate students. And I've run into them at conferences for years. So we were aware that we were doing not the same project, but closely related projects. And we agreed it's close enough related that we should point out each other's work when we wrote it up. But the next one that cited us interests me for totally different reasons. I've never met any of these researchers, but what I notice here is that within a year of when this project happened at Valpo, there are researchers in Madagascar reading our paper and building on it. So this is a project that's literally been read around the world. That was just at Source 2 years ago. And so no matter how into the math details you were, hopefully that gives you a good idea of just how far a project can continue, even beyond what we see today. And I think that's pretty exciting. And I think that's just one story. So I showed you a whole wall of photos of students with math posters earlier in this talk. Each of these pictures, to me, represents one of those other projects that I could tell you all kinds of discoveries that they made mathematically and where the project went from there. But I asked you to think about one more thing besides paying attention to my math story. We started out this talk thinking about how being thrown into a totally different environment with the coronavirus is an opportunity for a lot of discoveries. And I think being thrown into a new research problem is also an opportunity for a lot of discoveries on a lot of levels that are not just the math that you see in posters or in papers. And so let me think a little bit more generally with you about what are some of the other things you might be figuring out or benefiting from as you go through an undergraduate research project. To think a little bit more generally than mathematics, I'm going to borrow some ideas from an organization called the Council on Undergraduate Research, which really provides support for faculty who want to do research projects with students, but they also advocate for undergraduate research and for funding for it. And they also study what are the benefits of undergraduate research. And these are taken straight from their website. I have undergraduate in parentheses because I think a lot of these also apply to graduate research. And so if you're a student, you could be thinking through this list and going, how many of these things happened as I was working on my project? Did you maybe build a stronger mentoring relationship with a faculty member? That's a benefit you might not directly see on a poster, but I think an important one from going through a research project. Did it make you more likely to stick with your major and academic program? If so, that's a benefit. I think another big benefit or discovery that people make as they're going through a research project is they get more data about what they want to do in the next phase of their education or career. So maybe you got more data that made you more likely to go to grad school or help direct you on what career path you want next. Maybe you develop more critical thinking, creativity, or problem-solving skills. I know research methodology might not be the right language for every discipline, but maybe you got a better understanding of how things work in your discipline. And maybe it made you more innovative. I think all of these are great benefits of doing undergraduate research that you don't necessarily see reflected in our presentations today. That's discovery on a totally different level than the very specific content things we'll hear. And I think a lot of these are actually kind of externally facing goods. So a lot of these bullets, either directly or indirectly, might be something you put in a job application or on a resume. The one that strikes me as the most kind of internal and personal is this one that just went red. And to play with that a little bit, I'm going to share my current favorite definition of research. It actually comes from American author Zora Neale Hurston, who says research is formalized curiosity. It's poking and prying with a purpose. The thing that I really enjoy hearing in SOURCE presentations every year is that these research projects don't tend to be things that you just grinded out and computed. They're things that you actually got really curious about, and that curiosity really drove what was going on. And so that's thinking about some other benefits of undergraduate research in general. I want to come back to the specific project team I highlighted, because there's one more reason I picked them that I haven't mentioned yet. And it's because about a year after their project was done, I asked them to reflect on what they got out of it. And I'm going to share in their own words what they told me about a year after their project was done. One student says, most importantly, I learned math is collaborative. When doing research, math becomes a collaborative field where mathematicians are constantly pitching ideas to each other in hopes that together they can reach their goal. Another student says there's something so satisfying and rewarding about solving problems in a research setting. The results you come up with are novel. No one's ever done it before. Once you find a pattern and prove why it works, you've proven something that all mathematicians can use forever. And a third student says, I thoroughly enjoyed unleashing a new sense of self-motivation from the experience. The first thing I want to point out about all these quotes, and they are verbatim what that team told me a year after the project was wrapped, is that no one said the word permutation once. If you had talked to them at SOURCE, they would have told you all about permutations and patterns and ascents and descents and peaks, and that's fantastic. That is one level of discovery they made. But a year later in reflection, that's not actually what they're talking about. I actually see at least two big important themes going on here. And I'll highlight it by just grabbing key phrases to have a little bit of a cleaner slide on the next page. I think there's some important realizations about their discipline of mathematics that they might not have gotten from traditional classroom experiences. Realizing math is collaborative is maybe surprising if you're used to thinking of math as this is a thing I compute and grind out. And yet these students are realizing there's something to sharing ideas until you converge on the thing that works and trying on lots of perspectives. And that was a new realization. This quote in blue, you've proven something that all mathematicians can use forever, is showing realization that it wasn't just our project, but we were building on these previous results, and we've seen other people building on ours. They're part of this ongoing academic dialogue, which I think are some pretty fantastic realizations. There also were some more personal realizations here of unleashing a new sense of self-motivation. We're finding something so satisfying and rewarding. And I think those are really important aspects of self-discovery too, from trying new things out in a new context. And I know you might be looking at these quotes going, those seem kind of cherry-picked. I promise this is what this team said. But I will admit there have been some teams on previous projects where some people say, I feel really satisfied with the work we did. I'm proud of the results we did, but this has also told me I want to do different things next year. And they sometimes say that sheepishly, and I say, no, you're making informed decisions based on data and experience. That's actually really great. And so, as I wrap up my remarks and we get ready to turn it over to all of your presentations, for the students in the audience, I have some questions for you as I wrap up. I'm wondering, as you reflect on your project, what discoveries have you made in your project area? And I think a lot of you have answered that really well with the posters and audio files I've really enjoyed listening to this week in advance of today. I think you're well prepared to answer this. But I also know this has been a semester without a lot of downtime, thanks to the change to virtual learning and virtual research and virtual all kinds of things. So if you haven't had time to reflect yet, I'd also encourage you to think about this. What has doing a research project taught you more generally about your discipline that you might not have known if you had stuck to traditional classwork? And what discoveries have you made about yourself through the process of doing research? I think that there's probably as many different answers to these as there are presenters on today's program, and I think that's part of what makes them fantastic reflection questions. And so I look forward to celebrating with you today as you answer this first bullet throughout today's sessions. But I also wish you happy reflecting as you think about the second and third. Thanks for listening.
Thanks so much, Laura. That was great. And now we'd like to turn it over to you, the participants, for some questions. We've left plenty of time for that. Use the raise hand feature, and you'll be Your microphone will be unmuted so that you can ask.
Don't be shy now. Burkholder.
So when you're displaying like the different permutations as the left and right, does that make each permutation unique then?
Yes, if you're avoiding these two specific patterns, this is a bijection. So for each permutation, it's a unique list of L's and R's. And for each list of L's and R's, it's a unique permutation that avoids these two patterns.
Is it also a unique permutation for like the larger like 8 by 8 board that you made?
Oh yeah, so this scales up to permutations of any size. So if I go back to the Simeon and Schmidt theorem, notice it says that there are 2 to the n minus 1 permutations of size n. Encoding these as lists where you have 2 choices for each digit is actually an alternate way of explaining why there's a power of 2 number of these, because there's 1 permutation for each list of L's and R's. That's a good question to scale up.
Laura, I've got one. You represent each of your permutations by the list of R's and L's. Going in the reverse direction, if I just had the R's and L's, how easy is it to then reconstruct a permutation? Because it seems non-trivial to me.
So if you're willing to work from the top to the bottom, this actually, I don't know which column to put this dot in, but I know that the next dot should go to the left. So if you're willing to kind of scoot things over as you need more room, this actually is a recipe to read off. This tells me the first 3 dots should all go to the left one at a time of this. Yeah. So with some practice.
I know it's a little early, students, so don't be shy. Now's your chance.
Oh, I saw 2 more raised hands.
Professor Pudwell, I raised my hand. Professor Zigman, can I ask my question?
Jump right in, please.
So thank you very much. Learned a lot and really appreciated it. I don't know enough about math to actually ask an intelligent question about the research that you're talking about. My question has to do more with what it's like as a student doing undergraduate research, or maybe even your own research. Could you talk about a time when your expectations for research really foundered, or, you know, is there a time when you thought a project just really wasn't going well? Or, like, the basic question is, in research, how do you deal with failure?
So I would say if you're looking at things on multiple levels, there's always something to learn from an experience. Even if the math doesn't go quite as far as you were hoping for, there's always something that was learned. And so I guess I practice the art of refocusing. I mean, failure is a broad term. So how are you defining that? There could be personal things going on that are preventing me or other people from making as much progress as we want. And then that's not necessarily a failure of the project. That's a time to maybe readjust what you're focusing on as a person and then come back to research later maybe. But if there's reasons that the math is kind of running into a dead end, I guess one thing I enjoy is I generally have a family of problems to work on. And so if I'm getting really frustrated with one, I kind of practice the art of refocusing on a neighboring problem and then maybe coming back to the tricky one later. And so I'm not saying I don't show persistence, but I kind of have a cost benefit analysis where I go, if I've been stuck on this long enough, let me refocus on something else and come back to it. And sometimes the partial progress in a different direction is what encourages me or students to keep going. Does that address that a little bit?
Yeah, thanks. That was very helpful. I appreciate the response, Professor Pudwell.
Hi, this is Dean Susan Van Zanten. Thank you very much for a really interesting talk, Laura. Actually, you know, about something I don't know very much, but I learned a lot. I'm really interested in kind of thinking about the contrast between the first part of your talk and the second part of your talk. Okay. Where the first part, the discoveries that you focused on, a lot of the discoveries were kind of discoveries made by circumstance, by accident, if you will. Mm-hmm. Accidental discoveries, right? No one plans to stay home and teach their children and have these discoveries. The second whole part, I mean, research, and that great quote from Zora Neale Hurston is discovery comes from curiosity. You get obsessed about a question or interested, intrigued in a question. I'm wondering if you can reflect on the differences and maybe the similarities between discovery by accident, if it will, or circumstances, and discovery by curiosity. And kind of a secondary question here is, how do we cultivate curiosity? How do we get people to be more curious about things? And maybe that's related to the accidents of life as well. I don't know. Anyway.
Good question.
I think we might have lost Laura.
I think so. Well,
am I audible?
All right, go ahead, Laura.
Okay, so I should be in business now? So, Susan, those are some great questions. I will do my best at some initial thoughts. What I was starting to say was, I think even in kind of the discovery motivated by curiosity, that there's accidental circumstantial discoveries that happen then too. I can name multiple situations where a student's been working on a project and they happen to have read or seen something that inspires them to look at the problem in a new way. I distinctly remember a team of students I was working with in summer 2011 where they were stuck on a problem for so long, and by circumstance they watched a movie one night in the residence hall and then came back and said, I saw this on the wall in the movie and it made me realize this is what we need to do about our problem. And it's not the same as the circumstances living in a pandemic, but it is kind of discovery by accident, right? And so the problem was on their mind, and so they were more receptive to this new idea. And so I think sometimes it takes a combination of accident and curiosity to cultivate new understandings, and it's worth being open to both simultaneously. Oh, you asked a second question too.
Cultivating curiosity. How do we encourage people to be more curious?
So I think that really depends on the human, and I'm going to have a hard time giving a loaded answer or an answer that applies to everybody. Although I guess from a personal point of view or from observing students, the people who are the most curious are the people who keep already seeking out new experiences, and then it's kind of a feedback loop of you tried something new and it made you ask some questions which led you to something else new. And so I guess if we can find a way to encourage people to access a variety of inputs, whether it's things that they're reading or things that they're doing to try new things. I think the experience of trying new things is one avenue, at least for a lot of people, to become more curious.
Daniel, go ahead.
Yeah, Professor Pudwell, and this I guess is more of a content-based question on the research itself. It seemed like a lot of the permutations were binary operations where there was either a dot or there wasn't. Is there any relevance, or I suppose any way to consider a situation that is similar to that, but in a non-binary sense? So you could have a blank or a dot or a cross, say.
So I think, Daniel, in the third session today, you should go visit my research team from this year for a good answer to that.
Okay.
So Jake Roth, Devin Harris, and Austin Schnorr worked with me on something that has not just one dot per row and column in the grid. And that's one possible answer. But yeah, you just asked a curiosity question where you could talk about patterns in these structures that generalize permutations and see what comes out.
Thank you.
Yeah, you're welcome.
Thomas, go ahead.
Hello, Professor Pudwell. Was curious, like this honestly just came to mind because the permutations are represented in left and right.
Mm-hmm.
But can we do a similar thing, like going from column to column, doing up and down, and be able to count peaks and valleys that way?
So that is not the only way to encode those as lists with two letters. In fact, what's most advantageous, left or right or up and down, depends on the particular pair of permutations that you're trying to avoid. And so there definitely were other pairs of patterns besides the red one and the orange one I featured where we did encode with ups and downs or with other letters. It really depends on what the graph looks like. So that was kind of we needed to make a choice of something binary, and that's the one we wrote up. Did that address your question?
Yeah, it did. Thanks.
Dave, go ahead.
Hi, this is Dave Scupham from the biology department. And I want to, thanks very much for the presentation. That was very, very interesting. I want to talk a little bit about discovery as discernment. And I've had a number of students over the years, not many, but a couple, that have used my laboratory research as a way to discern whether or not research was really something that they wanted to do for a living. And a number of them decided, no, it wasn't. It wasn't for them. And I am always a little bit puzzled by that as someone who enjoys research, why that would be. But as I reflect back on that a little bit more, I realized this is a really important part of undergraduate research that I think is often overlooked. There are always students who decide, this really isn't what I want to do. I want to go off and do something else. So you have mentored a lot of students in your career. Have you had a few that have simply said, no, this is not what I want to do now that I've given it a shot? So maybe you could comment on that.
Absolutely. So I think when I was sharing student quotes from just this one team at the end, at least I meant to mention, I think I did, I've had some students who get to the end and say, yeah, this is really not what I'm doing next. And they always say it kind of sheepishly. And I don't think they should be saying it sheepishly because they're actually collecting data and experience to inform what they do next. And so, I mean, I'm a pure mathematician. Sometimes it means, no, I want to do something more applied, or I've realized I'm really passionate about this thing going on in my minor or my second major. I think this process of discernment is important, that if you're going to make a career doing research, it gets really exhausting to do if you don't have some amount of enthusiasm for the area you're working in. Mm-hmm. And so if you've realized, no, this is not really making me excited, I think that helps them make an informed decision where they can maybe refocus and find where they are more excited and enthusiastic. I still think that's valuable data that we shouldn't be dismissing. But I think the reflection process of what did I actually learn through this about myself, I think that's an important question, no matter what the answer is.
Thank you.
Well, thanks again, Professor Pudwell, for a really stimulating talk, for starting off SOURCE 2020. And for all those who attended, thank you for attending this session. You'll see on the screen our schedule for the day that includes now 3 sessions of student research presentations and meetings where you'll have a chance to actually ask questions and get feedback from the student presenters themselves. If you click on each one of those sessions, you see a list of about 30 to 35 student presentations. And obviously, you won't be able to visit all of those within the space of 50 minutes, but we hope you'll pick out a few and drop in and ask some questions of the student presenters and get a sample of what exciting things they've been working on this year. And then join us at 3 p.m. for the closing presentation. Thanks very much, and we hope you enjoy SOURCE 2020.